area that would cover, the B field would cover is going to be just pi r squared, pi a squared, the radius of the magnet.
Doesn't it, like, at the end of the magnet, doesn't it, like, magnetic?
Yeah, we are considering ideal case.
Okay.
We assume it's normal to the area. Yeah, we don't go into that complication. Of course, the magnetic field are gonna be, like that,
Yeah.
not just straight up.
Right.
So, but it's limited only to this area.
Okay.
We assume that the magnetic field outside this area is to be 0. So you can say mu naught m times pi a squared. So this flux at once you insert it here is going to be a mu naught m pi a squared. All right. Then after that, when you start to pull it, it starts to degrade. Okay. The second part is to plot the induced EMF. So over this period, what do you expect?
It's going to increase.
Yeah, okay, yeah, the flux is increasing, but induced voltage is always, you can see from here, negative of
Yeah,
change in flux, so you would expect, so if you plot, this is time, and this is delta V induced, you expect a negative voltage because of the negative sign here. Because of this minus sign, and that's delta V induced. Even if the change in flux is increasing, the flux is increasing, but because of the negative sign, you
It's
expect,
becoming more negative, right?
yeah,
Okay.
at some point in time you expect peak,
Right.
and then it does.
Because the flux stops changing.
Yes, stops changing. Then you would have flat over a certain period of time. Over this period of time. And then what happens? The flux starts to decrease. So, but because of the minus sign, you expect it to be something like that. Does that make sense? So I'm going to show you some project that we did a few years ago. The results, yeah, okay. So what you see here is just look at here. So what we have here is a big solenoid, and we mounted these magnets. The magnet that I just showed you. These magnets are mounted on a toy car. So this is the toy car that we mounted on these magnets, and this place is over by the basketball stadium. There is a tunnel connecting.
AMG is right beside.
Yeah, so that's in the tunnel. So we built this downslope where the magnet, slides. So, as you know, potential energy changes into kinetic energy. So as it goes in, the flux starts to increase and then remains constant. Therefore, short period of time, it depends on the speed. And then as it starts to leave out of the solenoid here, the flux starts to decrease. Then you would reduce. So this is what was measured. If you look at here, so this is the measured voltage as a function of time.
Colors,
Yeah, the
shots.
different colors represent, what do you think? Different what? Heights, yes. Because the higher the peak is the higher the energy you will induce, you produce. So in order to get more electrical energy, you have to release it from a higher elevation.
Why did yours start with the positive and then go to the negative? Is that just how you graph it?
No, it depends on which end of the magnet you are inserting.
Oh,
Yeah,
okay, that makes
yeah.
sense.
So if you reverse whatever end of the magnet you inserted, you would find a positive voltage and a negative voltage first, and then a positive voltage. And also it depends how you connected your oscilloscope, the polarity.
Okay.
Yeah. Okay, so this one, you see a longer period here for some, and shorter period where you have a voltage actually. So why do you think we get bigger period for this one, smaller, smaller, smaller? What did we change here? Yes, yeah. If when you change the size of the magnet, the longer period of time for this thing to slide through through the solenoid. So the length of the magnet, or you can say the period over which the flux is changing, the longer it is, the longer the voltage time that you see. All right, so now another example: if you want solenoid coil around an iron core, the iron is there to beat up the magnetic field. Place a metal ring on top and plug it in. The ring will jump several feet in the air. Why? Okay, in the example that we did, I think it was last semester, where we have a current carrying circular loop sitting at the end of a solenoid. We have shown that it would be pushed upward, right? So in that case, you have a loop that carries a current, okay? That carries a current sitting at the end of a solenoid. You saw that it experienced a force. Either depending on the direction of the magnetic field, it could be pushed up or it could be attracted down. But here, you put a circular loop, no current in it, but still you would be able to see that it's going to be pushed upward. Why do you think that's happening?
Supposing you change the flux.
Yeah, the flux changes. When the flux changes, induces a current, and that current would experience a force. So the question here is to describe why that's happening. So before you turn the source on, there was no flux, just the ring and the solenoid. So flux is 0. So at t equals to 0, at t equals to 0, flux is 0. But all of a sudden, you turn the current on in the solenoid, so you have, let's say, at t equals to t prime u